approximation for maximum matching in Python.
Yeah, thank you for the introduction. This is trying to work with Sepida and with our amazing intern Mohammed. Okay, so the problem is to estimate the size of a maximum matching in sublinear time. So we want to maximize the approximation ratio, of course, and we are aiming for runtime that is less than n squared. Okay, that's the problem, and is the number of vertices. The sublinear access model, so there are two models that one can consider. In the adjacency list model, the algorithm has access to the adjacency list of graph, which means that for every vertex, it knows its degree, and we can ask for like the ith neighbor of a vertex. In the adjacency matrix model, we ask whether, for example, vertices u and v are connected with anything. Okay, the reason why we estimate the size is that it is actually impossible to find the edges or to materialize explicitly any large matching in time that is less than n squared. Okay, this is the result by Parnas and Ron. Yeah, this is why we estimate the size only. Okay, so this is a fundamental problem in the fundamental model, but in case you need more convincing, then such an algorithm for estimating matching size can be used for also other things. So, for example, the recent works on dynamic algorithms for estimating matching size use such subroutines. Also, even more recent dynamic algorithms for maintaining a matching, which can use this to check whether some subgraph has a large matching before using time to construct that matching. And also as the subroutine in other problems like computing earth mover distance, mean cost perfect matching, or TSP or Steiner tree. Okay. Yeah, so what you want to do is you want to have the highest possible approximation ratio while minimizing the running time. So you're in this like 2D trade-off situation. And there have been quite a few prior works trying to map out this trade-off. So in terms of algorithms, I only discuss those that are today Pareto optimal. So there is the 1/2 approximation by Sohel-Bechnejad that runs in O of n time. You can slightly improve the approximation ratio, and then you pay a slight penalty in the running time. This is the Bechnejad, Rogani, Rubinstein, and Saberi. And Bhattacharya, Kis, and Saranurak on the other end of the spectrum show that you can slightly beat n squared time and then get almost one approximation. Okay. And that result is actually almost tight, which was shown by Bechnejad, Rogani, and Rubinstein. Indeed, you need almost n squared time to get close to one approximation. They also show that you need at least n to the 1.2 time to get 2/3 approximation. And then Parnas and Ron had also a second result, which shows that in order to get any constant approximation, even to the matching size, as we're doing, you need at least n time. So that also makes Sohel's result optimal in terms of running time. Okay, so this arrow shows, where you want to be in this picture. Yeah, so basically, now the issue is that all these improvements upon the 1/2 approximation or improvements to n squared running time are really small. It's like still very close to n squared runtime or still very close to 1/2. So it's important to know, what's in the middle here. And in the middle here is our algorithm. Okay, so we give such a somewhat substantial improvement in both of these parameters. So in particular, our result is that there is an algorithm that estimates matching size in n to the 1.5 time, and we have an approximation factor of 0.51. Okay. Our algorithm works in both of the models, so both adjacency list and adjacency matrix, and also it's simpler than the prior approaches that beat 1/2. Okay, so yeah, that's the result. questions so far? All right. Good. So let's discuss how we do it. I believe I hope I will be able to show the whole thing. Very influential result by Sohail, and something that we will use a lot is his algorithm that gives 1/2 approximation by estimating the size of a maximal matching. Okay, that gives you 1/2 and no better than 1/2. So actually it gives you more than just estimating the size. It comes with a local vertex oracle that for a vertex v that you query, it says whether v is matched in that fixed maximal matching in time O of d. So here m is some fixed maximal matching, and this is the average degree of the graph. Okay. Yeah, how do you use such a thing? Okay, it's quite simple. You just ask about a couple of vertices and extrapolate the matching size from that. If you want a multiplicative approximation, you need to ask about more vertices, but still it will all be in O of n time altogether. Okay, so yeah, that is a tool that we will use heavily. Okay, so yeah, how can we improve upon maximal matching? So we try to take inspiration from the semi-streaming model. So there are 2-pass algorithms that get better than 0.5. In particular, this is due to our very session chair and Kiran Naidu. Okay, so in the first pass, what we do is we construct a maximal matching M. Okay, and in the semi-streaming model, we're not claiming that we can do it. But then in the second pass, the idea is that we augment this matching by trying to find a lot of length tree augmenting paths. And the way that this is done is that we construct a maximal B matching between the matched and the unmatched vertices. So the matched vertices are given a capacity of 1, and the unmatched vertices are, let's say, given a capacity of 2. Okay. And then we return a maximum matching in M union B. And the idea is that if M was small, if it was a bad approximation close to 1/2, then we will find a lot of length tree augmenting paths, and in this way we can get something around 0.58 approximation. Okay, so more or less, this is what we want to simulate in sublinear time. Okay, the first challenge comes already at the very beginning in the first step, which is that, again, we cannot compute the edges explicitly of any maximal matching in sublinear time. So what we do instead is we say, okay, we will just keep the matching in our heads and then set up our GMM oracle, the vertex oracle, to know if you query a vertex, you can say whether that vertex is matched in M. Okay. For the B, we also cannot compute it, and we also set up an oracle to say whether something is in B. Now, the thing that's important here is that this oracle for B will need to operate in this subgraph between the matched and the unmatched vertices. So if it looks at some vertex, then it needs to know whether that vertex is matched in M or not, which means that it needs to call this inner oracle for M. Okay, this is why we call this first oracle the inner oracle, and the second one the outer oracle, because it calls the inner one. Okay. Yeah, this spells trouble, right? Because, okay, there are all of the inner oracle calls, but then each inner oracle call also takes all of the time, right? So that unfortunately leaves us with n squared. So need some more ideas, definitely. But okay, it's actually d squared. It's just that there are examples where both of these degrees are as bad as n, but maybe if we reduce the degrees, things will work out. So indeed, the first step of our algorithm is that we start by sparsifying the instance in order to reduce the degrees. What we do is we compute manually a matching in a subsampled graph. Okay, so we start with an empty matching, and for every vertex in the graph, we sample some square root n random neighbors of it, and then try to build a matching with this. And this takes time n to the 3/2. Okay. Okay, so what does this give? It gives some matching. It's not maximal in the whole graph. We cannot hope for this. And there will be some unmatched vertices that could have been matched. But what is nice is that in this unmatched graph, the blue one, which we call G prime, now with high probability, the internal degrees there are at most square root n. Intuitively, it like works out. Like if you had more of these edges, then something should have been sampled, right? Okay, great. But okay, we wanted to have a maximal matching to simulate that two-pass algorithm. So now we extend m to m prime so that m plus m prime is a maximal matching. Okay. Now m prime we cannot materialize, again, the same thing. So we set up an RGMM oracle for m prime. So m is built explicitly, we have it in memory, but m prime we access as an oracle. And then we try to augment m plus m prime with a B matching, the green one, like this. Okay. Again, we cannot build this B matching. We can only estimate its size. So we have, again, the setup of outer oracle that calls the inner oracle. Okay, still n squared, unfortunately. We are quite close, but not yet. Okay, why does this still run in n squared time? So the issue is that, okay, you could think that the inner oracle is great because it's in this subgraph which is low degree. But the problem is that it doesn't run in O of square root n time. It runs in O of n time. And this is because it does not know, it does not have access to the adjacency list of G prime. What we have is adjacency list access to G. And so if I am at this red vertex and want to find some edge that goes to G prime, maybe I'll have to loop through a lot of edges that turn out to go to M. Even though it's fast to check that it goes to M, I'm wasting time. So this can be done in O of n, but not any faster. And then unfortunately, the outer oracle will call the inner oracle also n times because like these guys might have a ton of edges to m prime and they might think that this is going down, but until you check by running the inner oracle, you won't know. So you take n oracle calls to the inner oracle and each one takes n time. Okay, so still n squared, but we will soon get, with just one modification, we will get down to a good running time. Okay, so our final algorithm, no more non-working stuff, I promise. This is the final algorithm. Okay, what do we do? So the first step, we do the subsampling step. So we build this matching M by subsampling, and then this G prime has low degree. Okay. Now we return the larger of two estimates. Okay, for each graph, one of them will be good. Either we take M as is, we don't try to augment M, we just try to augment M prime by finding this brown B matching called B1. Okay, or also we can think, okay, maybe M prime is like empty or this doesn't give any benefit. But so we also augment M by finding this green B matching B2. Okay, but then we just completely ignore M prime. Okay, so let's look at the approximation ratio. So if we think of a case where the maximal matching only gives a half approximation, as we usually do, so it looks like in this picture, then if M prime is large, then augmenting M prime, which is what we do in this first, in this case 1, will give us enough benefit. And if M prime is maybe small, then M is large, and then augmenting M will give us enough benefit. And if you do the math quickly, then you get something like 0.51 if you balance out the two cases. Okay. I don't want to dwell too much on that. The more interesting thing is the running time. Okay. So the second case is the easy one. There is only one oracle here, the one that computes or estimates the size of B2. This is because it's only augmenting M, and M we actually have access to explicitly. We have built it out in our memory, and so we can check if vertex matched is O of 1 time without calling an inner oracle. So there's just one oracle, so that runs in O of n time. No issue. Okay. What about the first case? That is more interesting. And the reason that it's going to work is that now both oracles actually operate inside this G prime, which is a low degree subgraph. Okay, let's look at that. Okay, so it seems that life is actually very good because we are in this subgraph that is of degree square root n. We have an inner oracle that runs in d time, which is square root n, outer oracle n time, square root n time. So that would give O of n runtime. But again, this would only hold if we had access to HSSC list of G prime. We don't. And okay, so maybe there is an issue because now if we are some vertex want a G prime neighbor, maybe we have to read the whole HSSC list to find one. O of n overhead would be very bad, then we're back to n squared. Okay, so we use two key properties of the RGMM oracle. The first is that at each step, it needs only a random neighbor of the vertex that I'm at. Okay. So, okay, if I'm at some vertex, I want to find a random neighbor of G prime. I'm going to sample random neighbors in G. Number of samples I need to find someone is at most n over my degree in G prime. It's okay. If we had all the degrees in G prime equal to d, then we would get something like, okay, d oracle calls of the outer oracle times d inner oracle calls, and this n over d overhead, that's n times d, and d is small, this is great. Okay. Almost happy. The only slight issue, maybe some vertices actually have small degree in G prime, right? Then the overhead can be O of n, and okay. But again, okay. Last thing, second key property of the RGM oracle. Okay, yes, this is bad if a vertex has low degree, but actually every vertex is visited proportionally to its degree, so that does not happen very often. Okay, this is a property that we also used in recent work on Steiner trees. Okay, and then actually what happens is the total runtime calculation looks like for each vertex, the expected time it gets, expected number of visits to it is this, and then we get this overhead, and it super nicely cancels out. So we really just get n to the 3 halves, and that is all. Okay, so just to sum up, our result is that we have an algorithm that estimates matching size to a 0.51 approximation factor in time n to the 1.5. And in terms of open problems, I just have natural ones for you, which is just to, go right and to the bottom in this plot. So concretely, let's say, okay, what time is needed to get a 2/3 approximation? Okay, thank you.
Yes. Could I also ask the next speaker to start everyone? Maybe just one question.
Mm-hmm.
Do people conjecture specific things here in this picture, or is this widely just open?
I'm happy to conjecture that in our running time, maybe you can also do 2 minus square root 2, like 0.58. I think this maybe can be improved without damaging the running time.
Okay, then thanks again.